Hello everyone, so today we're going to talk about the alternating series test. So alternating series are ones where basically the terms are alternating between positive and negatives. And the method of convergence is, sometimes there's what's known as absolute convergence, which is the kind of convergence we've been looking at so far. And then there's another one called conditional convergence, because things kind of alternate and they don't work quite as nicely. It's not quite a strong version of convergence, but we'll look at this now. If you ever get into an analysis class, then you're going to study this in more detail. But for now, I just want to paint it with kind of broad strokes purposes and go over a couple of examples. One of the big examples that we'll see is, like the harmonic series 1 over n, 1 plus a half plus a third plus a fourth, and that goes on forever. That diverges. But if you look at, say, the alternating, that's actually going to converge, right? It's definitely going to be smaller, so it would look like 1 minus a half plus a third minus a fourth, and so on. They alternate rather than containing only positive terms. So let's go ahead and look at this alternating series test. So what does the alternating series test say? So the alternating series and we'll be explicit. We'll say it's the sum of -1 to some powers. We'll say k plus 1 of a sub k converges provided 1. So the terms of the series are non-increasing. So if we only look at the positive parts there, 0 is going to be less than or equal to a sub k plus 1 is going to be less than or equal to a sub k for all k bigger than some index n. So you can always throw away a finite number of terms. So it doesn't necessarily have to start off decreasing, like, you might go 1, 2, 3, 4, 5, and then all of a sudden you start decreasing by dividing by 2, 5 halves, 5 fourths, 5 eighths, 5, and so on. And then it turns geometric after some portion. So you can always throw away a finite number of terms, but eventually you have to get it where the terms themselves, excluding the negatives, the positive parts are getting smaller and smaller and smaller. And then the second thing is that the limit, as k goes to infinity, of these terms that are non-increasing, they actually go to 0. So this implies convergence for alternating series. Don't confuse that with the divergence test. Remember, the limit of the terms going to 0 does not imply that a regular series will converge. But for these alternating series, it will. So that's important to note. Note that for series with only positive terms, the limit as k goes to infinity of a sub k equals 0 does not imply convergence. So, the first example we talked about, the alternating harmonic, this very quickly shows that it is a convergent series. Example, apply the alternating series test. I'll just abbreviate AST to show the series. I'm already trying to write the proof. So the series of, say, -1 to the k plus 1 over k, so from k equals 1 to infinity, converges. So the proof, part 1, clearly, so clearly 1 over k is bigger than 1 over k plus 1 for all k. So terms are non-increasing. And then 2, the limit as k goes to infinity of 1 over k equals 0. So by the alternating series test, this series will converge. So hence, by AST, the series converges. So that's all we have to do is demonstrate those two things, and we can find the whether or not a series converges. So really, no new techniques here. You just have to show that the terms at some point are non-increasing. So we've shown that here. Let's go ahead and do another one just for completeness. But again, there's no new techniques really here. So example. Determine whether, let's look at the series from k equals 2 to infinity of -1 to the k, natural log of k over k converges. That's not a question, it's a statement. Imperative statement at that. The first part is, what about the natural log of k over k? We want to determine if that is less than natural log of k plus 1 over k plus 1. So that's not so easy to do just by comparing consecutive terms. So one, let's consider y equals the natural log of x over x as a function. Right? If we do that, then what we can do is we can take the derivative, and the derivatives will tell us where things are increasing or decreasing, and that will give us a tool to determine whether or not that's happening for the series above, right? Because the integer points are just points on the continuum anyway. So taking the derivative, we end up with y prime. We're going to have to use the quotient rule here. So the derivative of the bottom, 1 over x, derivative of the top times the bottom, 1 over x times x, minus the derivative of the bottom times the top over the bottom squared, ends up giving us 1 minus the natural log of x over x squared. Okay, so where is that going to be equal to 0 at? So so let's just set up our test value region. Let's just do it the old-fashioned way. Well, so let's say this has a critical point at 1 minus the natural log of x equals 0. That is when x is equal to e, right? So the natural log of e is equal to 1, so that's when you'll have a 0 for that derivative. You can ignore the bottom, right? Because the bottom is just telling you where it's defined or not. You're not going to get a derivative of 0 there. Furthermore, it's at 0, and if you look at our series, we only care about starting at k equals 2. So what happens if we test the values of our derivative? We have two regions on one side of e and on the other side. So let's say we picked e to the 1/2 power. We'd end up with 1 minus 1/2 over some positive number, so you end up with a positive derivative on this region, and if you plugged in e squared, you'd end up with -1 over some positive number, so we end up with something negative. So hence the function is decreasing for x greater than e. So that tells us what we want to know. So that means for our series, the terms must be non-increasing for, let's say, k greater than 3. It might happen where they increase for the first term, but e is about 2.718, so we know we should get non-increasing after 2. So we're good there. So that actually is pretty much the more difficult part of this alternating series problem. So now we just want to look at the the limit of natural log of k over k, which I believe we did in the limit comparison. So we want to look at the limit as k goes to infinity of the natural log of k over k. In fact, we didn't even do this in the limit comparison. We did this in the L'Hopital section because the top's going to infinity, the bottom's going to infinity. So this is just going to be the limit as k goes to infinity of 1 over k, which is equal to 0. Again, I am implicitly using L'Hopital's rule, or explicitly using it, L'Hopital's rule on the second step there. Okay, so therefore the series converges by AST. So that's pretty much it. No new techniques, but gives us a way to handle convergence with alternating series. I'm not going to talk too much about the different types of convergence here, absolute or conditional, but know that absolute is the stronger version. So if something converges absolutely, it also converges conditionally. I'll just make a quick note, but we won't really go into it. So we'll say definition. So if you look at a series and all the positive terms converge, we say that the series of a sub k's converge absolutely. But if your regular terms diverge, but the absolute value converges, so if the absolute value here of these terms diverge, but maybe by the alternating series test converges, then we would say the series converges conditionally. So yeah, so if we look at our two examples, I think we did examples of both. So so e.g., what was the first example? We looked at the harmonic series, the sum with -1 to the k plus 1 times 1 over k. This one we would say converges conditionally. Why? Well, we showed it converged using the alternating series test, but if you took away the -1s, we would have the harmonic series, which we know diverges, so that would be the absolute value of that series. And then the second one we looked at converged, but if you looked at the absolute value of the terms, it would have converged as well. So if you looked at the, what did we have? -1 to the k plus 1, natural log of k over k. Well, it turns out both of those just, so I'm just making sure that's what we did. Yeah, so we had -1 to the k and natural log of k over k. Well, it turns out that natural log of k over k So actually, sorry, let me hide that. So the one we did was -1 to the k plus 1 natural log of k over k. We haven't talked about convergence of that series yet, but we did in the limit comparison talk about the natural log of k over k squared. So that would be one that converges absolutely. So this would be an example of something that converges absolutely, because the series that we looked at, natural log of k over k squared, converged. We used the limit comparison test, and if you remember, we compared that series, just the positive terms, to 1 over x to the 3 over 2. So that was a little bit of a tricky comparison. So anyway, so that's the definition of converging conditionally versus absolutely. And again, the remark, the one takeaway, absolute convergence implies conditional convergence. But the converse is not true. All right, so that's it for the alternating series test. This is Dr. Lennon signing off.